This session is for the hours that will be group 1, group 2, both of you, which we couldn't do it on Thursday and Friday due to the technical issues in Moodle. Now we're going to solve another example related to elastic zone using Poisson's ratio and the information in elastic zone. Now this question is a bit different, so we're going to discuss it. We'll understand how to deal with cases like this. For this purpose, we're going to solve 6.23. So the example says that, problem says that a cylindrical rod 100 millimeter long and having a diameter of 10 millimeter. So we have a cylindrical rod which the diameter and the length given to us. So for the purpose we have it, this is the diameter, the length of it 100 millimeter and the diameter 10 is going to be 100, and the diameter is 10 millimeter. It says that it's to be deformed using a tensile load. So there is a tensile load, so it's under tension, which the force is given 27,500 Newton. Well, it says that it must not experience either plastic deformation or a diameter reduction of more than 7.5 10 to the power minus 3 millimeter. So this specimen under 27,500 Newton tension with a diameter 10 millimeter, length 100 millimeter, it shall not experience plastic deformation. So it must be within elastic region. So we say that it must not experience either plastic deformation, that's one. At the same time, the diameter reduction. Why it says the diameter reduction here? Because we have tension. When there is tension, the length is increasing, the diameter is decreasing. So that's why I said diameter reduction, it's not allowed more than 7.5 10 to the power minus 3 millimeter. That's basically delta D. So delta D must not be more than 7.5 10 to the power minus 3 millimeter. That's two conditions that must be there with any material that you're using it. So he said that of the material listed as follow, which are possible candidates, justify your choices, choices. Now we have some materials here. Which of those materials can be used by satisfying the two conditions? Because you have load, you have the area, you have load, you have the area. So there are four materials. We have to choose between those materials. So maybe two of them can be used, one of them, or maybe all of them can be used. But what we have to prove that they are not experiencing plastic deformation, and the diameter reduction is not more than 7.5 10 to the power minus 3 millimeter. So in order to do so, what's given to us? Modulus of elasticity, yield, strength. Now we said that yield, it will be given as a strength. Why do you call strength? Because it's material property. I mean, yield point, you remember yield stress. The strength normally appears with the material properties, not with the applied. So there is applied stress and there is strength. So strength, it's basically a stress, but since it's a material property, it will be defined as a strength. So we call strength of the body. It's basically, you can handle, for example, this much pressure. The pressure is outside, the strength is inward, which is the material property. That's why yield strength appears most of the places. We'll have Poisson's ratio as well. Poisson's ratio for all of these alloys. Mainly they are alloy, because we said that alloy, they have much better properties than the pure metals. Now we have to make sure that to check those are satisfying the condition. So first thing, since we have the yield strength 200, 300, 400, 650, 650. Now we have to know which of those materials will be in elastic zone under the load that we have it. What does it mean? I mean, we have a load, and we have the area. So we'll be able to calculate the stress over this area. And we can calculate the stress within the material. And if the stress within the material it's more than the yield of any of this material, so we know that that material cannot be used. So I need you to understand there is an applied stress which is force over area. So if the applied stress for force over area is the stress is more than the yield, we know that that material, if we use that material, the material will be in plastic zone. So let's do the calculation, at least to find so we have the case here. We're going to find first area, which is pi over 4 10 square. That will be the area in millimeter square. If I calculate the area here, so I have 78 point 54, it's 5398, so the 54 millimeter square. The area we have it there, the area now we know that stress is equal to force over area. And we have 27,500. That's Newton, the bottom millimeter square. That's going to be megapascal. So 78.54. That's millimeter square at the bottom. So the result is going to give us megapascal. So let's calculate this one. So we have 27,500 divided by, so we have 350 megapascal, 350.14 megapascal. Now this is the applied stress over the material. So we have this stress inside the material. Since we know that yield is the place that, well, let's say this is yield. So we know that if a stress is more than yield, so this is the yield, stress more than yield will be in plastic zone. Stress below yield will be in elastic zone. So we know the regions like this. Now, which material will be useful in that case? Because we don't want plastic deformation to happen. So we're supposed to have a material that the yield strength must be more than this stress. Because let's say that your strength is 200 kilogram, and I will put 350 kilogram on your shoulder. Well, for sure you will yield when reach to this, even reach to 200 you will yield. So you cannot withstand this stress. Remember, this is applied stress. The yield strength must be more than this one in order not to have plastic deformation. So if you check the list that we have it here, we got 350 right there. And then you check here. So we're going to cancel out some of the materials that their yield is below 350. The first one, so we cancel out aluminum alloy. Why? Because it's 200. And we cancel out brass alloy because the yield is 300. I mean, the applied stress that we have, it is more than those two, so those cannot be used. You can say that aluminum alloy and brass alloy will experience plastic deformation because their yield strength is less than the applied stress. So this is the explanation. When you justify your choices, basically, they will say that aluminum alloy and brass alloy, their yield strength smaller than the applied stress, so they will experience plastic deformation. So we cancel the first two. So now it's between steel alloy and titanium alloy to see which of those two. Why? Because they're not going to experience plastic deformation. Yes, because the steel alloy yield strength is 400, still okay. If this is 400, it's below 400. For titanium alloy, 650, still safe. So for both of the cases we have it now, steel alloy and titanium, the material, those two material, if we use them, steel alloy and titanium alloy, with 10 millimeter diameter, 100 millimeter length, with the force we have there, they will be in elastic region. Now, between them, we have to check something else. What will be the second criteria that we have it here? The diameter change. So it says that the diameter reduction delta D cannot be more than 7.5 10 to the power minus 3 millimeter. Now we have to find delta D for both cases, or we can use this delta D and find Poisson's ratio. That will still be possible. We'll do anyway. So we're gonna find delta D for both of them. That's the easiest way between them to see that if we use steel alloy, what will be the diameter reduction? If we use titanium alloy, what will be the diameter reduction? So the delta D will decide which one will be used, or maybe both of them are possible. If their delta D is smaller than this one, because this is maximum, I mean, it says that it must not experience either plastic deformation or a diameter reduction more than this. So more than this is not allowable. So if the diameter change in both cases, steel alloy and titanium alloy, less than the delta D given, so both are candidates. So let's prove this one. Now we're going to start with steel alloy. So steel, we have the modulus of elasticity 207 and the Poisson's ratio is 0.3, so we're going to use those two. We no longer need the yield strengths. It was only for checking to see whether they are in elastic or plastic zone. So we need the modulus of elasticity 207 and 0.3 for steel alloy. First, we'll start with the steel alloy. Now the applied stress is the same. It doesn't matter because its area, it is the same. That's not going to change. So we're going to start with steel, which modulus of elasticity 207 gigapascal. And the Poisson's ratio 0.3. Why we need Poisson's ratio here? If you remember, we said that the reduction in the diameter is the lateral strain. And the only way to find lateral strain is through Poisson's ratio's equation. So what we're looking for? We're looking for delta D. So we're finding delta D. In order to find delta D, we need strain in x direction, which is the lateral strain, will be delta D over D0. Now we have D0, which is the initial one, 10 millimeter. We need to find strain in the x direction in order to find delta D. Well, in order to find strain in the x direction, as if you remember, we said that the only equation that we can find strain in the x direction is the Poisson's ratio equation. We cannot find it because it's not related to the load. It's related to the material property Poisson's ratio, which relate the longitudinal strain to the lateral strain. Well, since I need to use Poisson's ratio equation, and we know that the Poisson's ratio equation says that minus strain in the x direction over strain in the z direction. So you realize that you need strain in the z direction. Strain in the z direction. Well, we know that strain in the z direction can be found by what? By using the Hooke's law. Since we have the stress, we have the modulus of elasticity, we know that this equation can be used to find strain in the z direction. So we're going to find the strain in the z direction, bring it here, we have Poisson's ratio, we'll find strain in the x direction, then we're going to use the strain direction to find delta D. Straightforward calculation, we have it there. Just if you realize what you're doing, the rest will be easy. So we're starting with the finding EZ. So the procedure will be in this way: 1, 2, 3, going upward. I told you always that do reverse calculation to know what you need, and then from there you know what you need to find in order to get to that delta D. All of our aim delta D, so I reversed it. Now I know which steps supposed to come in the beginning in order to continue the rest. So for the first equation, so in the first equation we can write it strain in the z direction. We said that you can place everything inside each other. I mean, that's possible as well to make it the one step forward calculation. I mean, you can find, I believe that you can do this one. I've done a lot this in the class. So let me put everything inside each other. So if you want to do this one, to put everything inside each other, what will you do? You start with the last equation that you want to find. So you rearrange this one, you rearrange this according to the, what do you want to find? Sorry. So rearrange this one to what you want to find. When I find delta D, so delta D will be strain x times d0. So we write in this manner. We'll put everything inside each other to be one equation to find delta D. So delta D will be equal to d0 times ex. And ex basically will be what? Will be minus v times Poisson ratio times ez. So you can continue. So d0 stay here. Multiply this one. From the second equation, we can rearrange it in this manner. We're going to find ex, which will multiply Poisson ratio by the ez. So we'll have a minus there. Minus Poisson ratio times ez. Then still, I don't have ez. I'll bring ez from here. So this ez will be what? Will be sigma over modulus of elasticity. So I can further continue minus delta D. I brought the minus to front. Then Poisson ratio remains there. And Ez strain in the z direction will be sigma over modulus of elasticity. So I realize that this is the equation I can find delta D. Why it's better to make it like this? Because I have another example, another material to try it. Yes, it's easier to arrange the equation in this manner. So I can say at the end delta D is equal to minus original diameter times the Poisson ratio times the sigma over modulus of elasticity. Now what does the minus in front means here? This minus in the front, it means that reduction, and we already know that is reduction, because in tension we know that strain in z direction is positive, strain in the x direction will be negative, and negative strain in the x direction means delta D negative means that reduction will be reduction. So now we can just delete this part here and use the equation that we have. This rearrangement no need anymore. So we can just simply write delta D for steel, and we're writing it for, so delta D for steel here. Just pay attention to the units that we have. It says so minus 10, that's the diameter. Poisson ratio is at 0.3. And stress, we found it here, 350.14 megapascal. At the bottom as well, I need to have megapascal, so that delta D will come out as millimeter. So 207 10 to power 3 in order to be megapascal. 10 to power 3. So the result here will be in millimeter, because megapascal Poisson's ratio unitless. The 10 is the millimeter, so the result will be, now to see how much the result will come out here. So here we have 0.00507 507 millimeter. That's for one of them. Then let's write for the other one, then we will do the discussion at the end. So the second one will be titanium. So if I do for titanium the same way I'm going to do it, since I have the equation. So for titanium, delta D, I'm just going to bring the information for titanium, the information that we had, the modulus of elasticity will bring it, modulus of elasticity and the Poisson ratio, we're going to bring them, and we're going to calculate, then we will discuss to see what will happen. So according to the table that we have it, yes, modulus of elasticity for, it will be 107, I'm going to be clear now, 107 gigapascal, and the Poisson's ratio is 0.34. 0.34. So let's make it clear. We're going to use the same equation, since it's the equation, since we use it here, it's general equation. So we'll be able to find delta D also for titanium. So we're going to find using similar equation, which is still minus 10. By the way, there is a minus here, minus, that minus, it's reduction. It's reduction, I forgot to write it down. So 0.34 this time. Stress is still the same, 350.14, and at the bottom we have 107 10 to power 3 to be megapascal. So I'm going to delete this equation here, so no longer need it. So this value here as well will be minus. If I calculate this one, you see what will happen. Will be divided by 107, will be 0.0111 millimeter. Now we found the two delta D. One of them is minus 0.00507. The other one became minus 0.00111 millimeter. If I haven't done any mistake in the calculation, basically those two values we have them. So let's double check them. We have force with modulus, we have stress over modulus of elasticity, bringing it here, Poisson ratio, bringing it here, times D. That's going to be delta D. Now let's see what do we have there. It says that maximum supposed to be not more than 7.5 10 to power minus 3. So 10 to power minus 3, what will be the maximum delta D? The maximum delta D here, this is delta D, sorry. The maximum delta D says that 7.5 10 to power minus 3. Yes, 10 to power minus 3, if I write it down, so it's going to be 0.0075 millimeter. That's basically 7.5 10 to power minus 3, because you're taking 3 here, then you put minus 3 there. So if our delta D is smaller than this one, then it's acceptable. Now the case that I have it here, we found two of them. We found two. For steel, we found it to be minus. By the way, the minus, also this is minus. I mean, some say this is also minus because it's reduction. That's also the minus. Now this is the maximum. This is the maximum, we have it. The one that we have, we found it. One of them became minus 0.005, the other one minus 0.01. So here this is bigger than the 0.0075, so we cannot accept the titanium, so the titanium cannot be accepted. So still it's the only candidate that will be in the elastic zone, and change in the diameter delta D will be less than 0.0075 millimeter, which is 0.005 millimeter. So this is the case that when you're dealing with two sides, the Poisson's ratio and the modulus of the elastic zone, so you have to check in this manner to see whether the material that you're using, it will be elastic first, because we said that deformation or plastic deformation, shape change, it's not preferred. And at the same time, we have some limitations. And the limitation here is what? The change in the diameter must not be more than 0.075 millimeter. That's change in the diameter. So you realize that we solved this by using the Poisson's ratio and the yield strength in order to make sure that the material will be satisfying the two conditions that we have. So we can say that the steel is the only candidate, since the applied stress is less than the yield strength, which is 400 megapascal, and the change in diameter delta D, it's 0.005 or 7 millimeter, which is smaller than the delta D, the maximum allowable delta D, which is 0.075 millimeter. That will be enough for the elastic zone. You'll be able to solve any other cases that you have it. Remember, checking, if you're not sure you're in elastic, you check it. And the other things that you have to know, that if it comes to lateral strain, you have to use the Poisson's ratio equation to find the lateral strain and change in the diameter if it's required. In the next videos, we'll be talking about some type of modulus of elasticity, some theoretical about plastic zone. Thanks for watching.